Alright, here we are in our lesson about projectile motion. So there's quite a few pages here, but if I can scroll down to the bottom, let's just see if I can get there. I don't think I'll include all this in one video, but just as a reminder that this goes along with, if I look at it here, there is a projectile motion worksheet, and when you're done this, you should be going through questions 1 through 10 on that. And there are 3 MOPs, right, to be working on. So while you're working on the worksheets and while you're working through this video lesson, make sure that you do those 3 MOPs, the 7, 8, and 9. I think you'll find them really helpful and they'll help your conceptual understanding of what's going on. Okay, so there we go. First of all, what is a projectile? So you can think of a projectile at its most simple level as something that we just throw into the air. But in physics, we have a more specific meaning for that. It's more like an ideal projectile. We're pretending that the air resistance doesn't exist. Okay. Now, for a lot of objects like baseballs or something that's very dense, the air resistance is not very significant. So just remember, if we see the word projectile, here is our definition for it right now. We're going to say a projectile is an object upon which the only force is gravity. So anytime there's a projectile, there's there's the free body diagram of a projectile. Hopefully I've ingrained in your head already that this does not tell you which way the object's moving. Okay, this could be moving up, it could be momentarily at rest, could be moving downwards, it could be moving to the right, or it could be moving to the left. All we do know is that since the force of gravity is downwards, it must be accelerating downwards, so the change in velocity must be towards downwards. So if it's going up, it's slowing down. If it's going down, it's speeding up. Okay, so here's some examples of projectiles. The good old drop a ball from the top of a cliff. Okay, so now we have the different dots. You can imagine that the amount of time that goes by between each of these dots is equal. So maybe, that's t equals 0, and here is t equals, 1 second, and t equals 2 seconds. And you'll see by the distance is increasing that it is speeding up on its way down. Here's another example where a person throwing the ball straight up. Okay, and you'll notice the symmetry to this, and also in the other one where here the person's throwing it up, but in this case they're giving it a bit of horizontal velocity. Here it's almost straight up. If we did a straight up, we would actually only have one set of balls, right? Because you couldn't tell. Here they're going up and they're coming down afterwards. And you'll notice here this is the shape of a parabola. Just like the parabolas that you grew to love in grade 11 pre-cal. And if you think about the amount of time that it takes, this is going to be the halfway point, right? At the vertex is going to be halfway because of this symmetry. Also interesting to note is this velocity, the vertical velocity here up is going to be equal to this vertical velocity downwards. So anytime you're looking at the vertical velocities, there's going to be this symmetry that this velocity up is going to be matched later on by that velocity down, assuming that it's landing in the same horizontal plane that it took off from. If you're dropping it up from a cliff, clearly here it's going to be going down faster. Okay, so let's take a look at now two-dimensional motion. In grade 11, we only did really one-dimensional motion. So now we have 2 dimensions. Here's an example of one-dimensional motion, just straight downwards. This one is mostly one-dimensional. This is definitely two-dimensional. It's going up and down, and it's also going to the right. So the x direction, this would be known as the horizontal direction, and this is the vertical direction. So I think let's consider this last one when we think about this. So first of all, the free body diagram for all these is this direction here. Looks like that, force of gravity. So is there a force in the x direction? No, there's no 0, nothing. No force in x direction. Okay, and in the y direction there is a FG downward all the time. So this is in every example of a projectile. So how about, is there any acceleration in the x direction? No, because if there's no force in the x direction, there's no acceleration. How about in the y direction? Is there acceleration? Yes. And it will be negative 9.8 meters per second squared. Okay? Or we could say, if I erase this part, we could say down. Okay, 9.8 meters per second squared downwards. Every once in a while, we might be simplifying this and say 10 meters per second squared. Okay, when I was in high school, my teacher we weren't quite so good at metric, and it happened to be 32 feet per second squared. 32 feet per second. So if you see that, sometimes you'll know that's probably some teacher from the States or something, or from some time machine before Canada was fully metric. So just FYI. How about velocity? Is there a velocity in the x direction? Well, in this example, not really, straight down. In this one, a little bit. In this one, definitely there's some motion in the x direction. So is there velocity? Yes. But the thing is because there's no acceleration, it has to be a constant velocity. Constant velocity. Okay? Is there a velocity in the y direction? Yes. And it is a changing velocity. So when we do calculations in the x direction, which formula do we need? There's really only one formula we need, the one for constant velocity. And what is the formula for constant velocity? V equals delta d over delta t. So you recall that this is good. This is good for constant, or actually maybe I should put over here constant velocity. It's also good for average velocity. But if velocity is changing, and we don't know what the average velocity is, and that's the case over in the y direction, when we do things in the y direction, then we need our big 5. Because there is a constant acceleration. And what is that constant acceleration? 9.8 meters per second downward. And luckily we know them. We just derived them. So when we do this, I'm going to put a dx over here, and I'm going to put a dx over there because we're talking about in the x direction. So that's one difference we're going to get used to right away from grade 11 to grade 12. Now when we're doing this projectile motion, we're going to be keeping track of our x's and our y's and our components. Well, let's consider the path of a projectile. Let's shoot a cannonball at 20 meters per second, but pretend there's no gravity. So we're going to put this, we're going to get a gravity-free cannonball. They're very expensive. We will shoot it horizontally off a cliff that is 122.5 meters high. Well, here's the path. So this will be a t equals 0. It'll be there. Here will be a t equals 1. By the way, how far has it moved? If you said 20 meters, you are right. And here we go, t equals 2 seconds, so 2 seconds later, 3 and 4 seconds. So, you know, by the time 4 seconds rolls around, it's gone that 80 meters, it's gone that far. In the absence of gravity, an object in motion will continue in motion with the same speed and in the same direction. So we're going to assume that, that there's no, assume that the air resistance equals 0. Right? We're just going to say, that's, there's your basic Newton's first law, object in motion stays in motion. Now let's label Vx and Vy at each dot. Each dot is 1 second apart. Okay, so at this one over here, Vx, how far is it moving in the Vx direction? Here we go. We're going to say, Vx equals 20 meters per second. Over here, it's still going exactly. Vx equals 20 meters per second. Over here, Vx, I'm going to write it on top this time, Vx equals 20 meters per second, and so on. I'm just going to do the same distance here instead of writing it out, so you see that that's what it looks like. How about in the y direction? Vy is equal to 0. It's not moving it's not moving vertically at all. So even though it says here, label Vx and Vy, it's 0 at this point. So we can't really label it here, but how about we'll put it for the first one. I'll put it in red here. I'll say Vy equals 0. right? All the way through Vy is equal to 0. So if I was to label both Vx and Vy, I can't really put a Vy because it's not moving vertically. Okay, so that's what it looks like all the way through. Basically, it's going this way and this way. It's almost as if it's an object moving along a plane or on a table or something. If we turn on gravity, what will happen with the motion? Okay, so gravity is a force that causes things to accelerate downwards. How will the horizontal motion change? Well, force of gravity is going to cause a vertical acceleration, but not a horizontal motion. So not a horizontal change. How will the horizontal motion change? It will not. Stays the same. How will the vertical motion change? We're going to have a change in velocity of 9.8 meters per second down. In other words, we're going to have acceleration due to gravity. Okay, so moving on to the next page here. Example number 1. A ball is dropped from a cliff that is 122.5 meters high. We like that, 122.5. So how far does it fall after 1 second? So let's just say, okay, here's that guy. He's at the top, and this is 122.5. And so here we are, dropping the ball. That's at t equals 0. So at t equals 1, here it is over here somewhere. T equals 1 second. And we're wondering, how far has it fallen so far? All right, well, I think if we've got a constant acceleration, right? So this is a good situation for us to bring out our big 5. So let's consider all the things we know. When I see the word dropped, I realize then that V1 is equal to 0. So that's the first thing I know. V1 is equal to 0. I know that the ball drops for 1 second. I know that the acceleration is equal to negative 9.8 meters per second squared, and I want to know how far does it fall. So in other words, what is delta D? I don't know at this point what the final velocity is, so the one that I don't know is V2. So looking at your big 5 sheet, which equation does not have V2? The one that does not have V2 is the first one. So I'm looking at this, it says delta D is equal to V1 delta T plus 1/2 a delta T squared. Now since V1 is equal to 0, that means that this part is going to disappear. So I can take that out right away. So delta D is going to be equal to 1/2 times negative 9.8. So after we've done a couple of these, you realize that 1/2 of negative 9.8 is negative 4.9 multiplied by delta T squared, so that's 1 squared. So it will have a delta D of 4.9 meters. And that will be our answer. So the question is, how far does it fall after 1 second? So why is delta D negative? Well, it started from here, right, and it went down 4.9. So you could say it has fallen 4.9 meters. All right, so the negative part means that it's gone downwards, and that's what that fall means. Okay, how far does it fall after 2 seconds? Now really everything's going to be the same except for this 1 will change into a 2. Right, so if I see this 1 here and I see this 1 there, everything's going to be the same except that's going to change into a 2. So really here I'm going to say delta D is equal to, I'm just going to pick it up from this line here. I'm going to say minus 4.9 times 2 squared. Okay, so how far does something fall in t seconds? It goes 4.9 times the number of seconds squared. So it's going to be negative 4.9 times 4. So what is that? 5 times 4 is 20 minus 0.4, so it's going to be 19.4. 0.6 meters negative. Okay, so now we need to complete this chart. Okay, after how many seconds? What's the distance it has fallen? So after 0 seconds, it's fallen 0, and its height from the ground is still 122.5. After 1 second, it has fallen 4.9. After 2 seconds, it has fallen 19.6. Okay, I will pause, or actually you should pause, and I'd like you to complete this chart, and then I'll come back and fill it out for you. Or I'll fill it out and you make sure you did it right. Okay. Alright, in case you're not aware, so if the height was 122.5 altogether, for this next one you're going to do 122.5 minus 4.9, because that's how far it's fallen, so we'll get 117.6. Okay, I will just wait for a couple seconds and then I'll fill in the chart. Alright, so that you see the increased distances. After 1 second, 4.9, and then 19.6, and then all of a sudden it speeds up. And by the time 5 seconds goes by, the height from ground is 0. So you see why we picked 122.5, because it works out just neatly that after 5 seconds you've fallen exactly 122.5 meters. I'll put meters here. So it says go back to the cliff drawing and draw in dots to show the path of the cannonball with gravity. Draw in the velocity components for each dot. Okay, so let's go check it out. So we're going to go back to this one here, and remember at the time we said that Vy is equal to 0, but now we're going to say no, take 2. We're going to do this with some gravity involved. So here, let's consider, if I erase these ones so we have a bit of space. So our Vx is still 20 all the way across. To begin with, at time equals 0, v is still equals 0. And then at v1, well, I guess it'll have come down a little bit, right? It'll have dropped 4.9. And then here it'll dropped, what was our second value again? I can't remember. It'll have dropped a little bit more, and then here it'll drop a bit more. And then by the time it hits the ground, at 5 seconds. So that's its position. Okay, now let's think about the velocity here. The Vy is 0 still. Maybe I'll go to red. The velocity in the y direction is still 0. Here it's going to be going down slowly. Here it's going to be going down faster. Here it's going to be going along faster. And then just when it hits the ground, so before the ground applies any force onto it, so it's still a projectile, it's going down very fast. So I should actually show these arrows getting larger. So maybe I'll redraw this one to show it a little bit longer. So you should see a progression of these arrows getting longer. So let's consider here. So the Vy is going to be equal to Vy2 is going to be equal to Vy1 plus Ay delta t. So you see what I've done is I've taken equation number 4, and instead of V2 I'm saying Vy2. So in the y direction, it's after 1 second, it would be going its initial velocity of 0, so I only have to write that once. It would be going negative 9.8 times 1. So after 1 second, it'll be going negative 9.8 meters per second. So horizontally it's going 20, so I can still put the 20 here. There it's going 20. Here, horizontally, it's still going 20. And now, vertically at this point, it's going to be going 2. If I did this again, Vy2 is going to be equal to negative 9.8 times 2. So that would be equal to, what is that, 19.6. So here it's going Vy equals negative 19.6 meters per second. So you see how vertically it's increasing its velocity, while horizontally it's staying the same. And here it's Vx equals 20 here will be Vy is going to be equal to 29.4, and here Vy is going to be equal to 39.2 minus. So here is the path of the ball. So I'm trying to draw this nice path of the ball. And it is that familiar projectile path. And along the way, you'll notice that the horizontal velocity stays constant. There is no horizontal force acting on it, while the vertical velocity is changing. It's accelerating. Okay. Concept question here. It says, if we shot a bullet horizontally and at the same moment dropped a bullet from the same height, which bullet, the one that is shot or dropped, hits the ground first? So you just imagine what's going on here. So we got, here's the blue bullet. It's shot, horizontally real fast. So it's going to take this parabolic path to hit the ground. Okay. Now my other one is just dropped. It has no horizontal motion, so it's going to fall this way. Which one hits the ground first is the question. We will do this in class, not with an actual bullet, but with a bullet-like object. Don't worry, no actual students will be harmed in in this demonstration. All right, let's try example number 2. It says a cannonball is shot horizontally from a cliff at a velocity of 10 meters per second, and again the cliff is the same height. Okay, so let's draw a little bit of this one here. So, draw a diagram of the path of the cannonball. Okay, so here is the ground. Here is the cliff. There's the cliff, and it is our nice favorite 122.5 meters high. So from here to here is 125 meters, and we're firing this thing, and it's going to take this parabolic shape as it hits the ground. Done. That's part A. Check. Okay, it says separate the motion of the cannonball into X and Y components. Okay, so we'll put an X column here and a Y column there. Now just a reminder that the only motion here, there's no acceleration in the horizontal component, so we are only going to be using, in this way, V is equal to delta D over delta T. And I want to separate that out. I only want to talk about this horizontally, so it's going to be Vx here and dx there. So if you can see that, Vx is equal, this is the only formula we're going to use. So in other words, we're going to be saying, what's Vx, what's delta dx, and what's delta t? Now, time doesn't have a horizontal and a vertical component. So in this one, if we know 2 of those 3, we can find the third, right? That's how math works, okay? Now in the vertical, in the y direction here we're going to use the big 5. So, our big 5, we got V1, but I'm going to say Vy1 because I'm separated between x and y components. So this would be how fast the object is moving vertically initially, okay, at the beginning of the interval that I'm interested in. Vy2 is in the y direction, how fast, what's the velocity at the end of the interval that I'm interested in. Okay, and then delta t, ay, and what's left? Delta dy. So the one thing that we know all the time, this is the constant, this ay is going to be equal to negative 9.8 meters per second squared, because it's a projectile. We know that one. Okay, so now let's look at this particular, this is like, take this whole thing to the bank. You're going to use that so many times. Okay, so find all kinematic info for both components. So let's just fill it all out. So going back to the beginning of the chart, the cannonball is shot horizontally. So in other words, at the beginning, this has a Vx of 10 meters per second. And it has a Vy1 of 0. It is not thrown upwards or downwards. Okay, so let's fill that in. I got a 10 here, and I've got a 0 over here. Okay, the cliff is 122.5 meters high, so it's going to start here. This is the beginning of the motion I'm interested in. This is the end of the motion I'm interested in. Okay, so this distance of 125 is going to be how far it moves. That's going to be, so delta d, how far it moves in the y direction. So delta dy is going to be equal to negative 122.5 meters. So over here, delta dy, negative 122.5 meters. Why negative? Because it started from this height and moved downwards. Okay, and what about delta dx? Well, delta dx would be how far it moves horizontally in this direction. Delta dy, delta dx is that direction. Okay, so remember, you're thinking about displacement here. So sometimes in English we use this word and we talk about range. The range will be how far away from the cliff something's landed. We don't know that yet. Okay, so something that's really important for these questions is that delta t is going to be the same. So if you find delta t for one of these columns, you can import that value into the other column. Otherwise, they're totally separate. Okay, is there anything else? Well, looking at our big 5 over there, we already know 3 things, right? We know these 3 things, and I'd really like to figure out what delta t is, because once I figure out delta t is, like I said, I can import it over there. So I'm going to take the one that does not have Vy2 in it. So once again, I'm going to use equation number 1. So equation number 1 is, over here, delta d is equal to V1 delta t plus 1/2 a delta t squared. The only difference I'm going to make here is that I'm going to add all my little y's here, because I'm moving in the y direction. So I'll put a y there, put a y there. Vy1 is equal to 0, so I can just lop that off right away. And I know that delta dy is negative 122.5. It's going to be equal to 1/2 of negative 9.8, so it's negative 4.9, multiplied by delta t squared. And so I divide both sides by negative 4.9, and this part cancels out. This works out to, I believe, 25 is equal to delta t squared. So when I square root, I get delta t is equal to 5 seconds. And we kind of knew that the 122.5 meter cliff, it takes 5 seconds for an object to hit. So we got a 5 here. And now we're going to import that 5 over here, the 5 seconds. All right, so we know, what do we know so far? We know it took 5 seconds for that ball to hit the ground. How far does it move horizontally in this time? So if I use this equation to solve for delta dx, so this is what it looks like here. I got v is equal to delta d over delta t, and I want to solve for delta d, so it's going to be delta d is equal to v times delta t, in this case delta dx and vx, so it's going to be 10 times 5, so it will go 50 meters. So guess what? It's going to move 50 meters that way. So my answer here is 50 meters. Okay, is there anything else that we might, it says find all kinematic information. Well, we figured out all these things. The only one left is the Vy2. So if we're going to figure out the Vy2, well, we can use the equation where Vy2 or V2 is equal to V1 plus a delta t. And so it starts off at 0 and then plus negative 9.8. So I'm just going to write minus 9.8 times 5. So at the end of 5 seconds, 5 times 9.8 is what? 49, minus 49 meters per second. So that's how fast it's moving downwards at the end. So I'll put a minus 49 meters per second, even though I crossed it out before because I didn't need it for that earlier one. Wow, we've done quite a bit. I'm just going to take a pause here.